right, so this is review number 1, and the first thing I thought we should probably go over is the parts of a heating curve. Cooling curve is just the opposite of a heating curve. So just to orientate you, you have a sample of matter, pure matter, so it's like a compound or an element, and you're going to heat it up. Okay? If there are 2 plateaus, then you're undergoing 2 phase changes. But in this case, you would be starting with a sample in the solid phase. Notice on a heating curve, that's what this is. How can you tell this is a heating curve and not a cooling curve? Anybody know? Yeah.
It's starting at a lower temperature.
Yeah, you're starting at a low temperature and you're ending at a high temperature, so you're heating it up, right? Okay, a cooling curve would just look opposite this. You would be starting hot, and cooling it, that really wasn't very flat, and cooling it down. So a cooling curve would just have the opposite shape of a heating curve, okay? So at point A, you're really starting with the substance as a solid, and from A to B, during segment A to B, what you're doing is heating up a solid. Okay? Remember what the solid molecules do. And I tried to, on the bottom graph there, I tried to give you a picture just so that you could, because really this is about visualizing and what the heck's going on. So in the solid phase, the molecules are in a regular geometric pattern. They have a definite volume, they have a definite shape, and their motion is rather limited, right? There's very little distance between solid molecules, so they're super close together, and all they do is sit and vibrate, right? That's what's going on in the solid phase. And as you heat them up, they vibrate faster and faster and faster, so their kinetic energy speeds up until they have enough energy where they can begin to separate. And as they begin to separate, we call that melting. So if we go back to this picture, we can label this part here on our curve solid, but at point B, a very significant thing starts to happen. And at point B, the substance starts to melt. The temperature at which the substance starts to melt is known as the melting point. And if it's an element, of various melting points are given to you in Table S, physical properties of elements. So if you want to know, say for some reason you wanted to know, as a Jeopardy question, the melting point of aluminum, you can go to reference Table S, as in Sam. I have some of them here. Let's see. We're not really going to use this, but I just want to point out that the information is there, maybe. If you never noticed, the reference tables are in alphabetical order. Okay, so S is one of the last ones. They're A through T is how they go. But if you notice right here, see, it's sideways on mine because I don't know how to turn it. But see, that's melting point. So it's in degrees Kelvin, or Kelvin. And what did I say? Aluminum, because it's a Jeopardy question. Aluminum melts at 934 Kelvin. Ooh, it's pretty hot. It's about 298 Kelvin right now in this room. That's what it is. So to melt aluminum, you have to get to 922. What if I wanted to boil aluminum? I need 1363 Kelvin. So for elements, the melting point and boiling point are here. I tell you that because sometimes they might say, what phase does aluminum exist at STP? STP, standard temperature, is 273 Kelvin. Okay, so if we're at 273 and aluminum doesn't melt until 934, then aluminum would be a solid right now in this room, which is why there's things like aluminum foil, right? Because it hasn't melted yet. But if we're 950 in this room, aluminum would be a liquid, okay? And if it were, what was the other one? 1363 or 2740. I looked at the wrong one, excuse me. 2740 is its boiling point. So if it were 3,000 Kelvin in this room, then aluminum would be a gas. Okay? And they have different properties, solids, liquids, and gases. I kind of think you guys know that because it's been a while. Like you've been talking about that a while. So at point B, the solid starts to melt. Okay? From B to C, which is a flat part of the curve, that is a phase change. Okay, so on all the flat parts, that's where phase changes occur. So B to C is a phase change because
Angelique Jordan, please report to the office. Angelique Jordan, report to the office, please. Thank you.
Whew. B to C is a phase change because it's flat. And what we're doing is changing the solid into the liquid. What is the name of that phase change where you turn a solid into a liquid? It's called melting, okay? Notice that during this point, the temperature remains the same. Okay, while you're in a phase change, the temperature remains the same until every single solid molecule is turned into a liquid. So at point C, you'd have only liquid, and you would begin to heat up the liquid, okay? So from C to D, you're heating the liquid. Okay? And liquid molecules look a little bit different than solid molecules do. I call liquid molecules the ballroom dancers, right? So the molecules are farther apart when they're in the liquid phase, if you could look at them with your Miss Frizzle glasses. And they move around each other. So they're not just sitting and doing this. They still vibrate, but now I can't even walk and vibrate at the same time. But now they can move relative to each other. So it's like they ballroom dance. What's different about liquids than solids is that they do have a definite volume, right? So if this is 37 milliliters, okay, and it has a 37 milliliters, it is like cylindrical shaped, right? But if I pour it into a container that is a different shape, and you know this because you've made Jell-O molds before, say like this, is it still going to be cylindrical shaped? No, it's going to be square shaped, right? Or whatever shape that is. But is it still going to be 37 mils? Yeah, the liquid doesn't spread out and occupy the whole container. It stays 37 mils. Okay, if I remeasure, assuming that there is no liquid in here, you're still going to have 37 mils, but because it doesn't have its own shape, it takes the shape of its container. So liquids take the shape, they have a definite volume, but they have no definite shape. They take the shape of their container. Okay? So we heat the liquid, the molecules start moving, dancing faster and faster and faster and faster until something very important starts to happen. We call that boiling, until they begin to boil. So point D represents the boiling point. Okay, so this is when we have only liquid and we're heating it up, and point D represents the boiling point. Okay? So from D to E, that's flat. What's happening?
Phase change.
Phase change. From D to E. And the phase change this time would be from liquid to gas, which you can call many different things. You might call it boiling, or you could call it vaporization. Okay? You could even call it evaporation, but be careful, because if you're at the boiling point, it's a little more significant than evaporation can occur at any temperature. If Stacy took the lid off her liquid, her whatever this is, sparkling ice water, it's fancy, Stacy. If she took the lid off of it and left it here for a month, it would evaporate, even though this room got nowhere near the boiling point of water. Okay, it might not all evaporate, but some of it will. Evaporation can occur at any temperature. Boiling can only occur at the boiling point. So since we're at the boiling point for the substance, we call it boiling. If you called it evaporation, we wouldn't mark you wrong. You're close enough. All right, so then the flat part, we're phase change. Temperature remains constant. See, that's temperature. Temperature remains constant until every single liquid molecule is turned into a gas, right? And then that's point E. And from E to F, we are just heating a gas. Okay? So the gas gets hotter. And the molecules move faster. Gases don't have anything. Gases don't have their shape. Gases are like crazy ping pong balls or molecules in a pinball machine or something like that, right? If I were to exhale gas right now, it would spread out and occupy this whole container. Okay? Whatever the container is. It would even, some of it would even creep under the door because we're not airtight. Okay? So gases don't have their own volume. They spread out and they take the volume of the container, and they don't have their own shape. They take the shape of their container. So gases have no definite volume, no definite shape. Definite Volume, no definite shape, both definite. Definite volume, definite shape. They have their own shape. A question that comes up a lot is like, which of the following phases of matter spreads out and occupies its container? Yep, gas. Which has a regular geometric structure? Solid. Okay? Those types of questions come up. Which has the strongest IMFs? Intermolecular forces of attraction.
Solid.
Solid. Liquids have medium, gases have no intermolecular forces of attraction. Okay, so a couple other things related to these heating curves that we can kind of summarize. On the diagonal part, we know that there's only one phase on any diagonal, right? The first diagonal solid, second liquid, third gas. Just one phase is present, not two phases of matter, only one. Either just solid or just liquid or just gas, correct? Okay, we know also on the diagonal that the temp is increasing. And temperature is a measure of kinetic energy. Yep, good. I'm glad you know it. Temperature is a measure of kinetic energy. So if kinetic energy is energy of motion, okay? So if temp is going up, the molecules are moving faster, okay? Kinetic energy goes up. Kinetic energy is energy of motion. We have this on another page. We'll write it down. If kinetic energy is changing, then no energy is getting stored. What's stored energy called? Potential energy. So potential energy is constant. They do this a lot of times. Identify one region of the curve where potential energy is constant. Right? You pick a diagonal. Either A to B, C to D, or E to F. Okay. Identify one region of the curve where kinetic energy increases. Same answer, right? Wherever temp is going up, kinetic energy also goes up. Okay, now, on the flat parts, right? On the flat parts, we're in a phase change. So there's two phases present. Right? Depending on what phase change you're having. If you're between solid liquid, then those are the two phases you got. If you're between liquid gas, those are the two phases you have. Okay? What's happening to temperature on the flat part? It's constant, right? Temp is constant. And if temp is constant, what else is constant?
Kinetic energy.
Because it's a measure of kinetic energy. Temperature isn't heat. Get that out of your head right now. Temperature is a measure of how fast the molecules move, period. Okay, do they move faster when it's hotter? Yes. But temperature is not a form of energy. It's a measure of energy. It is not energy. Heat is energy. Temperature is a measure of energy. So low temp, not low kinetic energy. High temp, high kinetic energy. But temperature is a measurement. It is not a form of energy. So if temp's constant, kinetic energy is constant. So where the heck's all that heat going that we're adding? It's being stored, okay? It's being used to increase the potential energy. So notice that when temperature is changing, so is kinetic. When temperature is constant, so is kinetic. If kinetic's constant, then potential's changing, right? If kinetic's changing, then potential's constant. Potential and kinetic, only one of those can change. All right, on a cooling curve, everything's opposite, right? So let's pretend we're starting here. And you cool the gas, cool the gas, cool the gas. Well, then the temperature goes down, right? So kinetic energy goes down. You cool the gas until the molecules begin to condense. This is the condensation point. Notice they're the same temperature, right? Condensation is when the gas turns into the liquid. Okay? So the boiling point, which for water is 100 degrees, is also the same temperature as which it condenses. So what happens if you have water at 100 degrees? Both, right? What would it look like? Well, there'd be water condensing, right? Gaseous water, water vapor condensing, and liquid water boiling. Both processes would be happening. It's an equilibrium. They'd be happening at the same speed. Okay? So this is, you'd phase change, right? Until every single gas molecule is converted to liquid. Then you'd cool the liquid until the liquid began to freeze. This is the freezing point. That's the temperature at which the liquid starts to freeze. Notice what it's the same as. Melting point. So remember that table S? One of the questions Regents loves is, what is the freezing point of aluminum? And you go here, freezing point's not even on there. I'm just supposed to know that? You're supposed to know freezing point's the same as melting point. And so the freezing point for my aluminum was 934, right? Because that's its melting point. Okay? So if water's freezing point is 0 Celsius, right? 273 Kelvin, 0 Celsius. If this room were 0 Celsius, would water freeze or ice melt? Both. Yes, both, exactly. Some water molecules freeze, some solid molecules melt. It goes back and forth, back and forth, back and forth. And if you kept it at 0, it would always keep going back and forth. So you'd have solid and liquid water in equilibrium together. Okay? You've probably heard that word equilibrium before. All right. It's kind of messy. You got the idea? All right. We're going to do some questions with this in just a minute. There's a couple more things I want to mention on heating and cooling curves. I figured we'd go to that lower one. First of all, any phase change that involves going up the stairs. How do you make ice melt? Add heat. How do you make water boil? Add heat. These are all heat-requiring processes. We have an E word for that. If you absorb more heat than you release. Anybody know? Endothermic, right? Any phase change that involves takes a lot of energy to walk upstairs, doesn't it? They take a lot of energy to get up the stairs. Takes a lot of energy to go up the stairs. So these are all energy requiring. They require more energy than they release. They are endothermic. Heat requiring, right? There's another thing you should know about each of these phase changes going up the stairs. Look at the molecules. You go from highly structured and ordered to not very, right? What's the E word for disorder?
Entropy?
No, entropy. Enthalpy is heat. Entropy. So the entropy, the disorder. Have you guys done kinetics and equilibrium in Secom? Okay. The entropy, which is the disorder, increases. Down the stairs. I don't know, at the end of the day when I'm leaving, I got a lot more energy, right? Woo, I'm skipping down those stairs. Those are all energy releasing processes. Those are exothermic, and the entropy goes down. The disorder goes down. Okay? So you should know that about those heating curves. Do I have another heating curve on the other page or no? Let me see. No? Okay, good. There are a couple other things that I just want to label. We can calculate heat. We can calculate the heat needed to melt once we're at the melting point, or vaporize once we're at the boiling point. So we can calculate the heat required for those phase changes. Okay? The first one is called fusion. Okay? Q equals MHF. We're going to get to these equations in a minute. Okay? Heat of fusion is a constant. M is mass. Q is heat. Again, we'll get to those equations in a minute. But this is the energy needed to melt when you're at the melting point. That's significant when you're at the melting point. So it's not from the beginning until here. It's like once you get here, how much energy you have to put in to completely melt it. From the start of melting to the end of melting. Okay, not from the start of heating. Once you're at the melting point, so for ice, 0 degrees, till when it's done melting, how much heat do you need to put in? We can calculate that with this equation. Q equals MHF. I'll show you how to do that in just a minute, because I know that's why y'all came. Forgot those equations. Vaporize, same deal. You can calculate the heat needed to vaporize. That's this line, right? And you use this equation. Q equals MHV. Now again, didn't we say that boiling's going up and condensing's going down? So the heat needed to boil would be the same as the heat released when condensing. And the heat needed to melt is the same as the heat released when freezing. So you could also use those, although they don't normally ask it that way, to calculate the energy released during condensation, which you'd use this one, or the energy released during freezing, okay, which is usually this one. So there's two of our equations. If you're not on a flat part and you're not in a phase change, you could still calculate heat. So I could calculate the heat needed to go from, I don't know what temperature this is, say 5 to 10 degrees, right? Just when I'm in the temperature changing part of the curve, I can calculate that energy, but that's a different equation. When the temperature is changing and you're on the diagonal, any diagonal, you use Q equals M times C times delta T. And we'll define those variables, and I have examples for you, okay? Q equals M times C times delta T. That would be on any diagonal, guys. MCAT, I call it. Some people say triangle. I'm going to write it here for you. Any diagonal gets that, okay? So when you're not in a phase change, when you don't see any phase change words like melt, boil, vaporize, condense, you use that equation, okay? So anytime they ask you to calculate heat, you can use these equations. Now sometimes, flip to, I think it's one of your last pages. Oh, and so you see, oh, I may not have put this question in here. These equations that I just gave you, MC delta T, MHF, and MHV, they're right in your reference tables. You don't have to memorize them. Table T is your equation table, and look what they're under. Heat, right? Heat is energy. Okay? So you use this first one when you're not in a phase change. No phase change words. When temp is changing, when you're on the diagonal. When you don't see any phase change words. You're just heating it up or cooling it down. It's not undergoing a phase change. You use this second one, this guy, when you're freezing or melting. So if you see words like melt or freeze, then you use the second one. And you use the third one when you're boiling, and the V word for boiling is vaporize. So if you see that word, or condense. And again, I'll walk you through a couple of examples. That's typically what we're going to use them for. Now, if you look at the variables, everything's defined. So Q is what we use for heat. The typical unit for that would be joules, capital J, joules. Mass is measured in a unit called grams. So if you see grams, you know it's mass. These heat of fusion, heat of vaporization, and specific heat capacity, those three are all constants for a given substance. Like they never change. That's what it means. So if you're water, they're given to you. Those constants, if you're water, are given to you here on table B as in boy. There's heat of fusion. That's your HF. It takes 334 joules to melt 1 gram of ice when you're at its melting point. That's what it means. It takes, that's the heat of fusion. Takes 334 joules to melt 1 gram of ice once it's at its melting point. Well, what if you had 10 grams? Well, you take that number times 10. Q equals M, your mass, HF. So it takes 3,340, right? That's all you do. That's it. Okay, if you had 5 grams, you take this number of water, melt it times 5, or melt it times 5. Multiply it times 5, okay? This number is your heat of vaporization. Again, this is all for water. This is just for water. So if it's some other substance, you're either going to give it to you or you're going to have to calculate from your equation, Okay? But for water, they won't even give you these numbers because they expect you know where to look for water. So I always tell my students, if it seems like you don't have enough information, ask yourself if it's water, and then go to table B and pull out the constant that you need. Okay? Heat of vaporization is much greater. It's 2,260 joules. Again, that means it takes 2,260 joules to boil or vaporize 1 gram of liquid water. At its boiling point. So it's already at its boiling point. So what if you're cooking pasta tonight and you need to boil 100 grams of water? Well, then you're going to need that number times 100. You're going to need 2 million. Is that right? 2 more zeros?
Yeah.
Okay. 2 million. Is it? I don't know. Whatever. Add 2 more. Multiply that number by 100. 200, I don't know.
226.
Thank you. 226,000 joules to boil 100 grams of water, which I'll tell you what, 100 grams of water is this. So imagine how much energy it takes for you to cook your pasta. Lots, right? That's only 100. You're probably doing about, what did you say, 10 times that maybe? 5 times that? It's a lot of joules of energy it takes to make that pasta. Okay? To even just boil the water to cook your pasta. So for water, it takes more energy to boil than it does to freeze or melt. Okay? Sorry, did you get splashed? Okay. That's all right. I won't melt. I'm not that sweet. Specific heat capacity is used in the diagonal one. Q equals MC delta T. That's your C. That's your C. Okay? Specific heat capacity is your C. It takes 4.18 joules to raise the temperature of 1 gram of water 1 degree Celsius. Because now the temperature is changing, right? When you have these two equations, you do not use temperature. Temperature is not involved. Okay? They're going to give you a temperature, but that's just to clue you in that you're at the melting point or the boiling point. Okay? Delta T is change in temperature. It's your final temperature minus your initial temperature. Okay, these guys have funky units. Heat of fusion and heat of vaporization are joules per gram. Change in temperature will either be degrees Celsius or Kelvin. It doesn't really matter. You don't have to do any conversions here because the temperature change in Celsius is the same as the temperature change in Kelvin. And specific heat capacity has a super funky units. They're joules per gram degrees Celsius. Okay? Or joules per gram Kelvin. Only because you can use the units sometimes to identify what the heck they're giving you. Before I show you a problem and we look at one of those, a lot of times you'll get a short answer question that says, which is greater? Ready? Which is greater, the heat of fusion or the heat of vaporization, and how can you tell? Which is greater, the heat needed to melt or the heat needed to vaporize, and how can you tell? What's greater? Heat of vaporization is greater. Okay, most people get that part of the question right. It's the explanation part they get wrong.
The line is longer.
That's it. The line is longer. It takes more time and therefore more heat to vaporize. Okay, you know what kids say? It's at a higher temperature. No, temperature isn't heat. Temperature is kinetic energy. Okay? So the heat of vaporization is greater for this substance because it takes more time to vaporize than it does to melt. Okay? That's it. All right, let's try some problems. I think you're ready, right? Do we have some blanks to fill in? Look at temperature is, let's fill these in real quick. A measure of kinetic energy. It's not heat. It's not energy. It's a measure of energy. As temperature increases, kinetic energy increases. They love those questions too. Which of the following samples has the greatest kinetic energy? And they're going to give you volume and mass and phase. You don't care about any of it. You pick the one at the highest temperature. Kinetic energy is temperature. Get used to that. So kinetic energy is energy of motion. Potential energy is stored energy. Remember, energy is conserved. It cannot be created nor destroyed. So if you're adding heat, either the kinetic energy is changing or the potential energy is changing, not both. So if kinetic energy is going up, then potential energy must remain constant. Only one can change at a time. One form of energy can change at a time. Okay? So if potential energy is increasing, if kinetic energy is increasing, potential remains the same. Okay. I believe we have, oh, this is an interesting one, and then I have a whole bunch more practice. Let's look at this question. If heat is added at a constant rate of 500 joules per minute, find the heat of fusion and the heat of vaporization. Okay? So they're asking you for heat, they're asking you for those constants, right? They're asking you for HF, H sub F, and H sub B. Now, we don't know that this is water, so we cannot go to table B. But we can get these from the graph. And sometimes they'll ask you to do that, is to calculate the heat from the graph. What's important that you realize or that you recognize is this. Every minute is 500 joules of energy. Remember where heat of fusion is? This is HF. How many minutes is HF? Long. How long does it take to melt? 2 minutes. It starts melting at 2, it's done melting at 4. So the heat of fusion is 2 minutes of worth of adding energy. And each minute you add 500 joules. So if every minute's 500 joules and it takes 2 minutes, then how much energy have you added? I can do that one in my head. 1,000, right? So the heat of fusion here, the energy, it's actually a better way to say it. The heat needed to melt, it's really not the heat of fusion, but it would be 1,000 grams, 1,000 joules, excuse me. It's not really the heat of fusion, but we can calculate it. The energy needed to melt is really what it is. Okay? We can do the same thing with vaporization. Now that looks like it begins at 6 and ends at 9, right? So this is your HV in here. So it takes 3 minutes to vaporize once you're at the boiling point. And it's 500 every minute, so that would be 1,500 joules. Okay, so it's very rare that they ask it this way, but they could. Okay, you could be expected to get the heat of vaporization or the heat of fusion off the curve. Okay, and in that case, I think I found one like that. Actually, we'll turn to it in your packet. I think I found one like that. I think it is question number, and if you're at home, you'll just have to kind of follow along because I didn't put these questions in. But I believe it's question number, hold on. Oh shoot, maybe I did not. Oh, I did. I really didn't swear I saw it. I guess not. All right, I'll give you one next time. I know I saw it, I just may not have printed it for you. So never mind if you're following along at home. It's not in there. Okay? All right, let's try a couple calculation-based questions. So look at number 1. If you go to the next page, I have a bunch of, these are all Regents questions. You know what, let's build our confidence a little bit. Look at number 9 first. Do number 9 right now. Also do number 12. Do 9 and 12, which I consider pretty easy, or should be rather now. And then we'll go to a calculation question. 9 and 12. We definitely won't be able to do all of these in the time we have left. Or maybe we will. We'll see. right, so we're going to do an energy calculation. We're going to look at number 1. When I read a problem that has numbers, every time I see a number, I stop and identify what the heck that number is. A 10-gram sample of water at 23 degrees absorbs 2009 joules of heat. What is the final temperature of the water sample? 10 grams is the first number. I write down my givens, right? I am given 10.0 grams. What is gram a measure of? Everybody say mass. Mass, good. So grams, when they give you grams, that's your mass. And mass is always abbreviated with an M. Okay? So they've given me mass. It's water. You might want to write down that it's water, because that's super important later. Because if it's water, do y'all remember what I can use? Yeah, very good, whoever said that. I can use table B, okay? You can use table B if it's water. At 23 degrees Celsius. Now, here's a big misconception. Students often think that is C in the equation, specific heat capacity. Degrees Celsius is a unit of temperature. Okay? And so this is a T. Now, it can be one of 3 T's. It can be my starting T, my ending T, or my changing T. I have to read it more to figure out which T it is, but I know it's a T. All right? Absorbs 2009 joules of heat. Joules is J, capital J. Now, if you forgot what letter we use for heat, you should just go to your reference tables. Because notice it says heat is Q. See it right here? Heat is Q. Q is measured in joules. So when you see joules, that's heat, that's Q in your equation. I forgot where I was. Q. So that's my Q. What is the final temperature? So I don't see any other numbers. So then I write down what the heck they're asking me for. And they're asking for final temp, right? What is the final temp? That's my TF. They want to know T final. Okay? So now, I guess before we look for an equation, we got to identify, was this 23? Was that how much my temperature changed, or what my sample was starting at? Starting at. Because it says water at 23 degrees, right? Not water changed by 23 degrees. So if it says at, that's your starting temperature. That's your Ti. Okay. So we're given heat. We have Q. We have joules. If you don't know what equation to use, you're going to go to this one and hopefully you play eeny, meeny, miny, mo and pick the right one. Or you're going to ask yourself, are there any phase change words here? Did you see the words Stacy, freeze, or melt? No. Okay. So I'm probably not using this one. Did you see the words, Megan, boil, or vaporize, or condense? There's no phase change words. If there are no phase change words, ladies and gentlemen, we use that one, the top one. There's not a phase change word in sight. So we're going to use Q equals M. Now, when the letters are written next to each other, it just means multiply. So M times C times delta T. And now we plug and chunk. Once we write down what's given, we write down what's asked, we find an equation to help us, we just simply plug in what we know. We know Q. Agreed? 209. We know M, we already identified it. I forgot what it was, but what is it? 10. Okay. Now, we don't have the change in temperature, and right now we don't have the C, which is specific heat capacity. So we have 2 unknowns, don't we? We don't know how much the temperature changed by. Okay? We could, delta T is really equal to TF minus TI. And we could plug that in, but I don't recommend it because most students don't have the best math skills. So I would recommend just leave that out, and I'll show you what to do to get TF in a minute. This is the hardest question they could ask with this. Okay? What I do know is that you can't have 2 unknowns. And so it was important that I wrote down over here that this was water. Because if it's water, I can get the constant for water that I need, the C, off table B. The C is 4.18. So I'm going to plug that in for my C. Go ahead. Did I hear ask her? No?
No.
Okay. 4.18. And I'm going to solve for my delta T. That's going to be my X. Delta means difference. It means change. It's not triangle T. Okay? So I'm going to solve for delta T. So I multiply 10 times 4.18, and I get 41.88 times delta T. And then I divide both sides by 41.8. And what does my delta T turn out to be? Somebody have a calculator? I put some calculators out too.
It's 5.
It's 5? It's 5. Okay? So what that means is my temperature changed (5 degrees Celsius). Okay? Now, I started, do you remember what I started at? My initial temperature? Okay, there we go. My initial temperature was what, 23? Okay, I'm adding heat, right? Is that what I'm doing in this problem?
Yeah.
It absorbs 209 joules of heat, so I should get hotter, right? Okay, so if I started at 23 and my change in temperature is 5, I will add 5 to that, and that will give me my TF, which should be 28 degrees Celsius. The reason I add the 5 is because in the problem it said heat was absorbed, right? If it said heat was released, then I would have done 23 minus 5 if it said release. And my initial temperature or final temperature would have been 18. So if it's absorbing heat, it's going to get hotter and you add the delta T. If it's releasing heat, it's going to get colder and you subtract the delta T. Okay? Try number 3 right now on your own. But I will just kind of write down what's given and what's asked. The first number I see is the number 100. And the unit that follows that is grams. So I know that you know that 100 grams is mass. That's our M, right? That's mass. I also know that it says of water. Okay? So I know I can go to table B for whatever constant I need. Whether I need HF, HV, or C remains to be determined. When the temperature of the water is increased from, so I'm starting at 30 degrees Celsius, that's my TI, my starting temperature, to 45 degrees Celsius, that's my ending temperature. To get my change in temperature, I just subtract them. My delta T is my final minus my initial, always. Final minus initial. So 45 minus 30, I saw Kayla had 15 degrees Celsius on her paper, is your delta T. Are there any more numbers? I don't see any. So the next thing I go is, what the heck do they want to know? What are they asking me for? Where's the question word? What is the total amount of heat? Okay, so they're asking me for heat, which is Q. Are there any phase change words? Anybody see melt, freeze, boil, vaporize, condense?
No.
So I am using that first equation. Q equals M times C times delta T. I have M, what was it, 100? I have short-term memory here. C, since it's water, I can go to table B and look it up. 4.18, and my delta T is 15. So now all you do is take 100 times 4.18 times 15. And what do you get when you do that?
D.
Choice D?
6,200.
6,200, or some number close to that. 270 joules of heat. Okay? Look at number 22. It's the last one I want to do with you. I said I wanted to do 21 too, but I think you got it. I have the answers. Do you know that? The answers are attached. The answers to every question are on the very back. So, see them, Stace? Yeah, the very back page is all the answers. So if you go home, because I know we're running out of time, your mom might be waiting in the parking lot or whatever, just tell her we're going to do one more together. And then you can go home and forget about it while you eat dinner and then try some more practice. And then you'll know if you're getting them right because all the answers are attached. Okay, that's okay. Pay attention. Look at 22. Calculate the heat released when 25 grams of water, we know grams is mass, it's water, which means I can use table B. 25 grams of water freezes at 0 degrees Celsius. So obviously we have a temperature. Again, I don't know. We're at that temperature, so it isn't the change. So we can call it TI if we'd like, right? That's all the numbers. What do they want to know? Calculate the heat. So they're asking us for heat. Heat is Q. Now, do y'all see any phase change words? Melt, freeze. Oh, freeze. Do you see freeze? Freeze. Then we are not using that first equation. If we see freeze, I don't even know where I'm at anymore. If we see freeze, hello. There you go. Freezing, we use, you can't see it because I crossed it off. Q equals MHF for freezing. So all we're going to do, and I want you to see this because kids screw this up all the time. I mean, mess this up all the time. We're going to use Q equals M times HF. Your M, that's not where they make their mistake, 25. When you have phase change words, cross out the temperature. Do you know why they gave you that 0 degrees? Don't say it to confuse you. They're really trying to help you. They're hoping you go, oh, freezing. We're in a phase change. I know water freezes at 0 degrees Celsius, but you're never going to use temperature, ever. For boiling water, best they're going to say 100 degrees Celsius. That's where kids, usually you don't plug in 0 because your answer would be 0, right? People realize, oh, something's weird there. But where you screw up is on the vaporization one when they tell you at 100. And then you plug in the temperature. You never plug in the temperature, okay? You have to go to table B and get HF for water, which is 334. So make yourself a note. No temp in phase change ones. You do not use temp in the phase change calculations. All right? So you take 25 times 334, because remember it takes 334 joules to freeze. 334 joules are released when 1 gram freezes. Well, you're freezing 25 grams. So you just multiply that number by 25. And what do you get? 8,350. Okay? 8,000. So that's your answer. 8,350 joules. Let me tell you this. I really recommend, because we only have 10 hours of review together. It's not very much time, and I want to cram as much information down your little throats or in your brains as I possibly can in those 10 hours. So really take a break from this. Tomorrow, the next day, try a few problems. If you have questions, I'm available anytime. Come see me during roll call. Come see me during third period. I'm free. My lunch is 10th, and I have a study hall 6, 7. So I'm free. Roll call, third, 6, 7, or 10. All right? If you go home and try these and you're like, oh, I had it when you were doing it, but I forgot. Can you show me one more time? That's all good. Okay? I want you all to be very successful on the Regents exam. Everybody masters, right? Mastery for all. And then you get lunch. And then I take you out to lunch. That's how it goes, right? All right, guys. It's been a pleasure.